In this video, we're going to talk about a very important type of integration. It's called U-substitution. Before we learn how to do it, I want you to be able to recognize when you can do it. So this is the setup we're going to look for, and it's going to show up in all sorts of different ways all year. But every single time it's going to have one thing in common. There's going to be some sort of inside function. It could be cosine with an argument inside of it like this. It could be e with something fancy in the exponent, or ln of something, or a lot of different things. What we need to see, though, is whatever that inside function is, we need its derivative to also be in the integrand, waiting on the outside. Now, you might be saying, wait, the derivative of x squared isn't 2x? Sorry, isn't x? You're right, it's 2x. That's okay. Coefficients we can fix. We'll talk about that in a minute. But the main idea here is what we're looking for is the inside function with its derivative on the outside. As long as we see that, we're going to use this fancy thing called U-substitution. So let's take a look at what U-substitution looks like. First, we're going to look and see if we can identify the setup we want. Do we have an inside function? Yes, we have this being raised to the fifth power. That makes negative 3x to the fifth minus 1 our inside function. And importantly, its derivative is waiting for us on the outside. We're going to need that in a minute. So once we have our setup, we recognize we can use U-substitution, and then this is how it works. First off, what you're going to do is define U. U is the inside function. You have to make sure you say this. Don't try using U-substitution without writing down what you're doing. Once we have identified that U, we're going to find its differential. This is a two-step process, which if you want to skip the middle step, be my guest. But the two steps are find the derivative of U, which is just a simple polynomial, so we use the power rule. Hey, great, that's what we wanted, because that's what's in the integrand already. And then to turn that into the differential of U, instead of just the derivative, we very simply just multiply both sides by dx. And we call this the differential of U instead of the derivative of U. What you might notice, hopefully, is that this differential, negative 15x to the fourth dx, is in the integrand. It's split up in two different places right now, but that's not a problem. It's all multiplication, so I don't really care how split up it is. You might also notice that the U that we have here, of course, is also in the function. So what we're going to do next is make two substitutions. We're going to put U and du into the integral instead of all those things with all the x's. So we're going to rewrite our integral as the integral of, I'm going to hold off on the negative 15x to the fourth for just a second. It's the integral of my green negative 3x to the fifth minus 1 to the fifth. Well, that's just U to the fifth power. And now the yellow negative 15x to the fourth dx, well, we just said that's equal to dx, du. So we make our integral into something that we can actually integrate using some of our basic rules. The integral of u to the fifth in respect to u is u to the sixth over 6 plus c. So we just integrated with respect to u. And we're not going to leave our answer like that because we weren't looking for an answer in respect to u or in terms of u. We want an answer in respect or in terms of x. So we're going to put the x back in. But all that means is substituting that u out again and putting the negative 3x to the fifth minus 1 back in. And that is our antiderivative. We'll take a look at another couple of examples. This one looks a lot longer, but it's not any more complicated. We again want to recognize the inside function I'm calling this an inside function because it is being raised to the 1/5 power, so it is inside of that exponent or that radical, if we want to think of it that way. And we need to make sure that the derivative of that inside function is waiting for us outside. That's what we need. Is that what we have? Yeah, the derivative of e to the 4x minus 4 is pretty close to 2e to the 4x. Let's see if we can figure that out in just a second. So again, we'll define our u as the inside function, and finding its derivative. Be real careful about the chain rule and those coefficients there. So the differential that we're going to want to put in is 4e to the 4x dx, which we almost have. We have 2e to the 4x dx. We just need 4e to the 4x dx. As long as the only thing that's missing is a coefficient, it's okay. We can put a coefficient in. We can change the coefficients as much as we want. The reason why we can do that is you're allowed to put coefficients in and out of an integral as much as you want. And you're allowed to multiply by 1 wherever and whenever you want. So I can multiply this integral by 2 over 2. I'll just put the 2 inside the integrand and the over 2 outside the integrand, outside the integral. And what I'm doing is multiplying by 1, which means is obviously okay because I'm always allowed to multiply by 1. And the reason that helps is because now the 2 times 2e to the 4x, that together makes 4e to the 4x, which we'll then substitute out. So now that 2 is a part of my du. And the e to the 4x minus 4, that's my u, so I'm going to put my substitutions in. Now, important to note that the substitution still has a 1/2 in front of it. This 1/2, it still comes down. Once you put a coefficient in front of the integral, it's there to stay. So we have 1/2 times the integral of, I'm going to save my yellow part for afterwards. I'm going to put my green e to the 4x minus 4 raised to the 1/5 power times du. And again, this one is a simple power rule, so I can call that 1/2 times u to the 6/5 power over 6/5 plus c. And then over 6/5, you want to kind of get used to doing this real quickly in your head. To be honest, if you do it where you skip the over 6/5 and go straight to times 5/6, that's totally fine. So I'm going to take that 1/2 and multiply it times 5/6. And so then my final answer, and I forgot to mention this on the last page, but for the final answer, you don't really want to say that, well, I mean, you can say that this equals and then do your substitution. But what I really want to have in here is I want to have my original question, the integral of 2e to the 4x times e to the 4x minus 4 to the 1/5 power in respect to x. All of that equals, and now I'm going to do my substitution. I'm going to take my u out and put my e to the 4x minus 4 back in. 5/12 times e to the 4x minus 4 to the 6/5 plus c. And that's your final answer. We'll do one more quick one because it leads to a cool property that you have to know. We're going to do the integral of sine of x over cosine of x. Sorry, that was missing. That's a typo. And we're going to do it again with the u substitution, which requires, again, we notice an inside function whose derivative is in the integrand ready to be taken out. Now this one's a little bit tricky to look at because there's a sine in there and its derivative is cosine. And there's a cosine in there and its derivative is negative sine. And remember, the negative is not a problem. We can always fix coefficients later. Well, so which one do I want to take out? Well, the answer to that question is the only one I can take out is the sine of x, because the sine of x times dx, that's in the numerator. I wouldn't be able to take out the cosine of x from the denominator. So that means that my inside function is going to be the cosine of x, because its derivative is the sine of x, or I should say its derivative is the negative sine of x, which is pretty much waiting for me to cancel out in the numerator. So du is negative sine of x dx, and we can fix that negative sign the same way we fix any other coefficient we're trying to fix. If we need a negative in here, that's no problem. I just need to put a negative out there also. Multiply by -1. And because I'm multiplying by -1 twice, I'm really just multiplying by +1, which doesn't do anything. So we can rewrite this integral as the integral of, I'm going to take my yellow negative sine of x dx out and call that du. I'm going to take my green cosine of x out and put in a u. And then we're going to integrate, you can say du over u, or you can say 1 over u du. And to do that, we remember what we said the other day. Oh, I'm sorry, I forgot my negative, which is still there. What we said the other day, which is that the antiderivative of 1 over u is ln of the absolute value of the argument plus c. Of course, there's still a negative there. And so we can say that we can plug our u back in here, our green cosine of x, which I forgot to make green. We can plug that back in now and say that the integral of sine of x over cosine of x in respect to x is equal to the opposite of the ln of the absolute value of our u plus c. The reason why we care about this is, and a lot of you probably recognize this already, that sine of x over cosine of x, well, that means something to us. Sine of x over cosine of x is tangent. So what we've just found is the antiderivative of tangent of x dx. And before we go ahead and memorize that, I'm just going to point out that it's not usually memorized looking the way we have it right now. It could be. There's nothing wrong with this. But usually what people do is they take this negative sign and they put it, remember, coefficients in front of a log can be written as an exponent inside of a log. So we could write this as the positive ln of cosine of x to the negative first, which is not the inverse of cosine, it's the reciprocal of cosine, which we know to be secant. So we can call this the ln of the absolute value of secant of x. And that is the way you're going to memorize the antiderivative of tangent of x. And it does become very useful later this year.